Okay, we're back to Lucky Lecture 14 now. We made it through 13 without too much of a problem. And at the end of last question, there was a great tease that I think timed us out right on time. But it was really related to a question as how corrosion is related to our water to cement ratio and why we would we would limit the water to cement ratio based on corrosion. And I'll take a couple seconds here before we jump into the slides, and I'll answer that question. But what I wanted to do, we'll actually spend quite a bit more time on this later on in the semester. But the basic idea, if we go back to review from our last, some of the concepts from our last class, we said that on our x-axis we've got our water to cement ratio, where we've got our high water to cement ratios all the way over on the right-hand side. We've got our low water to cement ratios on our left-hand side. And we said if we're just worried about something like our compressor strength, we would see the compressor strength drop off as we increase the water to cement ratio. Now you remember that I mentioned the graph from Ken Hover, and we'd actually seen some similar graphs a little bit earlier in the semester where we had permeability. I could use K, or I'll actually write out permeability so that we all know what we're talking about here. And we saw that the permeability, and I'll try to use a different color here. I'll make our permeability blue. We saw that our permeability drops down dramatically as a function of water to cement ratio, much more dramatically. The curvature is much more dramatic than we had with our strength. And the basic idea here is that when you have a much higher water to cement ratio, you have a higher capillary voids, you have a higher volume of capillary voids or capillary pores, and what we'll end up with is on our surface of our concrete we'll have our reinforcing steel some distance below, and we're going to typically refer to this as our cover distance, and our cover distances in our concrete are typically going to be about 1.5 to 2 inches to 3 inches, somewhere in that range. So we're looking at protecting the concrete. And when you took reinforced concrete class, you probably remember that this was a number that seemed somewhat arbitrary, and they talked about the cover concrete, and then there wasn't a whole lot more discussion if it was anything like the reinforced class that I had. But what this is really up here to do is, this is here to protect the steel. So the cover is really there to protect the steel and to keep things from getting to the reinforcing steel. And the water to cement ratio basically dictates the pores that are going to be above the reinforcing steel. And if you've got a lot of porosity, it's going to be much easier for things like chlorides to get into the reinforcing steel. Now, so when we've got a very high water to cement ratio, we've got a high porosity, these chlorides get to the reinforcing steel very quickly, and once you get a significant buildup of chlorides at the reinforcing steel, that's when corrosion is going to start to take place. So the real link here between water to cement ratio and corrosion is the speed at which it allows things like chlorides to get into the system. It's really related to how fast things are going to be able to flow to get into the system. And that's what you see for almost all of those tests that we were talking about. That number of 0.4, 0.45, keeping to come back. 0.45 on our sulfates, how fast our sulfates are getting in so they can be reacting with the cement. Freeze thaw, how fast our water is getting into the system, how fast it can saturate. Here we're looking at how fast the chlorides are getting in, so it's really related back to the permeability of the system. So is that... So to jump back in today, what I wanted to do is, while we were talking about water to cement ratio, I wanted to go through very quickly and talk a little bit about some of our chemical admixtures. Many different types of chemical admixtures are available. One of the most frequent classes of admixtures that are out there are air entrainers that we were talking about. The second one that's out there are really ones that are put into the system to improve workability. As we mentioned before, we've sort of got this age-old battle of controlling our water to cement ratio because it's going to dictate the permeability, the pore structure of our system, versus we want something that's easy to mix on site, easy to place on site. And we'll see chemicals that are actually added to the system to really sort of help that fresh properties of our concrete. These are commonly referred to sort of by their proper name. They are water-reducing admixtures. By people who do this on an an everyday basis, you will hear the term plasticizer used quite frequently. Plasticizers are going to be known by most people. If you go out onto a construction site, you'll hear people talking about adding a Super P. They're talking about a super plasticizer being added to the back of the truck, so that's really what we're talking about here. Chemical admixtures are going to be controlled by ACI 212, and one of the things, and we'll talk a little bit about this, but admixtures come in a variety of sizes, shapes, colors, and smells. So you will see that there will be all types of different colors, and actually a lot of these colors are put in to make sure that we know that they are chemical admixtures and are of a specific class. Now, one of the things that I'll point out here is this is a picture under a microscope of cement and water. So what you will notice here is that the water in this particular case is sort of this light gray area, and these cement particles are these dark gray things that look a little bit like continents. So probably if we spend enough time looking around in here, we'll find something that, I don't know, maybe looks a little bit like Italy, or these things that look like continents. These are actually cement. This is actually cement in the system, and what you will notice is that there is this great big thing over here that's cement, but there's also this particle here that's cement. And what happens is this cement that I've drawn out here that looks kind of like that I mentioned, is Italy or a continent. This cement is not actually one particle. This is a collection or a group of particles, or a flocculated set of particles, and they're basically all sticking together. So if we looked around the house to find things that help things not to stick together, I think everybody here has had that one crazy sock where about 11 o'clock in the morning you reach to scratch your arm, and all of a sudden you pull out a sock that stuck to everything else in the laundry. One of the problems with something like static cling, you basically have a surface charge, and that's what's going to make that sock want to stick to everything else in the dryer. Well, in order to get rid of that problem, you add something like your fabric softener into the system, and that fabric softener is static. It's going to help you to reduce static cling in the overall laundry. You can actually do the exact same type of thing inside of your concrete. Instead of adding bounce to the system, though, we may be adding a different type of material that's going to act to alter the surface charges on the different particles and allow them to not want to stick together, change their attraction to one another. So we're going to get rid of these lumps or these great big islands, these fluffy masses, and we're going to start to get a system that is much more dispersed. So if we look at a comparison of these two systems, what you could see is the top is sort of the plain system. On the bottom, we see the system that's containing the water reducer or the dispersing admixture. So what you can see on the top is that we have these systems that are really clumping together, where on the bottom we've got a system that's much more finely distributed, and it's much more dispersed because the chemical is getting in there and helping to keep those particles from coming in contact with one another. Now, the big benefit is when you start to form a flock, what you're going to end up with these flocks is you're going to end up with big spaces between the flocks where the flocks can't move over top of one another, and this big space we will go on to refer to as a capillary pore. These are the pores that are inside of our system. We're going to end up with a lot of empty spaces because all these larger particles aren't going to fit together nicely. So what we can actually do is we can use a water reducer that can keep the particles from clumping together, and that can typically help us by removing some of the water out of the system and getting the system more densely packed, getting the cement particles closer together because they're not sticking together anymore, and they're able to move around a little bit more freely. Now, there are really what I would call three progressions of water reducer admixtures. There's probably a fourth one that's coming on, and it's really going to be bad because I'm going to have to find a new superhero to put on my three levels of performance. But really the most common types of admixtures that are out there, we can really represent with Homer. Homer Simpson here is sort of the common man, even though he and Super Pig went on to conquer the world. Homer is really sort of our view of the common man, and he's going to really represent our average everyday water reducer or plasticizer. And here what we can see is for these particular admixtures, we're going to be able to reduce the water by about 5 to 10%. inside of the system. So we can actually reduce the amount of water by 5 to 10%, and this is a pretty typical admixture. These, while they were known as early as the 1920s and 30s, they are used heavily in other industries. They really start becoming popular in the construction industry, 1970s, early 1970s. The only thing I would say before that took place, there were some very weird 3-lane roads that actually used water reducers, and we'll talk a little bit about these later on in the semester. The next step up is sort of a little bit more high-performing admixture, but it's a mid-range admixture. So it's not really the common man, but it's not sort of a fantasy person. It's a real person, much like Rocky was a real person and helped us to defeat the Cold War, and then he went on to make another 37 movies after the classic here. But this is sort of a little bit better overall product, not perfect. The last version here, you're going to see that the amount of water that can be reduced goes up dramatically. These are typically referred to high-range water reducers and super plasticizers, and you're going to see here that these are going to be the area where a lot of the developments are taking place when you start to get into real high-performance concrete, so you get into self-consolidating concretes. They're really looking at different chemistries. They're really looking at this high-range water-reducing admixture category. Now, I say this, we're going to actually spend an entire lecture talking about water reducers, what they do. We'll spend a lot more time talking about these. But I sort of go through this to give you a little bit of an idea on how we would start to adjust for water, much like we were talking about a little bit in the last lecture. But here, I've taken another table from one of Ken Hover's articles in November version of Concrete International in 2002. And Ken sort of gives you a graphical view of some of the typical adjustments that you would want to make to your water content. So the basic idea is if you were to go just straight up and down throughout this graph, this is sort of a 0% adjustment, and then you could start making some of the adjustments that I mentioned before. You could adjust for the aggregate shape. So if you have smooth, round particles, you would put less water in the system to account for that. If you have more flat or elongated rough particles, you could put a little bit more water inside of the system. Better aggregate grading, you're going to get less porosity in the system between the aggregates. You could get away with a little less water. Air entrainer, we know, is going to reduce the amount of water. Normal range, mid-range, high-range water reducers, you can see sort of the expectation of the amount of water that you would reduce. And then you've got some other factors here, different types of cements. This, again, is a graphical way that you can start to get a handle on some of the factors that you can be considering when you start doing your mixture proportioning process. Question?
Are those able to balance out each other on the other side?
Like if you had, let's say I've got silica fume, which may increase by 10%, and I use a mid-range water reducer, and that decreases by 10%, I come back. Yeah, that's essentially the overall idea here. What you would do, and we'll talk a little bit more about this when we go to sort of rapid mixture proportioning, you would come through this graph and you would say, well, maybe I get, I've got a really rough aggregate, I'm going to add 1% here. I've got air entrainer, so let's say I subtract 6% here. I've got a mid-range water reducer, so maybe I can subtract another 8%. I've got silica fumes, so maybe I add 10%. And at the end of the day, you total these up, and I'm almost embarrassed to total these up right now because it'll be recorded forever that I can't find out that minus 14 plus 11 gives me a negative 3% reduction, and then it'll go on for infamy that I can't add these numbers together, so I won't tell you that it's a 3% reduction in the water content. Other questions related to that? You want to see me do more math in my head?
What does it do to you pick your water cement ratio and then you decide whether you want to do these admixtures, and then you're changing the water content because you added these admixtures. What does it do to the strength properties by reducing the physical amount of water in there?
Well, by reducing the amount of water, you're really dictating the amount of paste that's inside of the system. So when we talk about water content, we're talking about the total amount of water that's in the system. We're talking about the paste. When we're talking about the water to cement ratio, we're really dictating the pore structure, which is dictating things like our strength. So they're sort of two separate issues.
So I guess which one do you do first? Do you choose these admixtures first and then do the water cement ratio? I thought this.
Right, so what we've done here is we're looking at our adjustment of our water. We've selected our water to cement ratio. The next thing we're going to do is go on into our cements.
Oh, okay.
And really what you need to do is you need to look at all of these sort of at the same time and jump ahead. Step 6. Now the beautiful thing when we start to go from step 6 on is there is very little art left. At this point, we've made all the decisions, we've made all the hard choices, and here is where I would say that this is the sophomore engineer's dream, because there is no more thinking. It can be automated in an Excel spreadsheet, so everyone is excited about this because we all get the same answer, and we can have a right answer at the end of the day. So everybody really likes this. Determining the amount of cement, well, the water to cement ratio tells us the weight of the water divided by the weight of the cement. So if we already know the water content, we know the water to cement ratio, which we've gotten from step 5, we can now use all of our advanced calculus to determine the amount of cement that's inside of the overall system. So an example of this, we said that we had a 0.424 water to cement ratio. We were going to use something like 275, 280 pounds per cubic yard of water. We could go through the calculation and find out that we would have 660 pounds per cubic yard of our cement. The only thing that we really need to think about at this point is we need to double check to make sure that we've met whatever minimum specification there is on the amount of cement that's inside of the system. Step 7, we can start to go ahead and we can start to look at estimating the amount of coarse aggregate. And in this particular case, you are going to jump in and there is a line that is missing from this table. Sometimes it appears, sometimes it doesn't. Today it didn't appear, but it goes... It jumps right through the graph where I've just drawn it, separating the maximum size of the aggregates from the millimeter to the inch size. What we have here is we've got the finest modulus listed in our different columns. We've got our maximum size aggregate, and then we've got a number, and this number in this table doesn't mean a whole lot to us right now, but we will see this in a couple seconds what it actually means. For our particular case, we had a finest modulus of 2.8. We had an 1.5 inch maximum size aggregate, so we might pull out a value of 0.71. Now the real question is, what does that 0.71 mean? That 0.71 takes us back to if we started to look at our concrete where we were proportioning it by a cubic yard at a time, that 0.71 really represents if we were to just take the aggregate and dump it into a box that was a yard by a yard by a yard, it would fill the box up 71% of the way. That is sort of the volume that's just occupied by the coarse aggregate, but what I will mention here is there is space in between those particles. There's space where the sand is going to go, there's space where the paste is going to go, but that 0.71 really gives us an idea of the bulk volume that coarse aggregate is going to take up. So we could go through now and we could calculate out the actual volume, and we're going to start to do what basically comes down to an accounting procedure where we're going to say I need 27 cubic feet if I'm going to make a yard of concrete. I can multiply that by 71%, and I would have aggregate by volume that is 19.17 cubic feet, and this is the bulk volume. If I know my dry rotted SSD dry rotted weight is 100 pounds, I could calculate out the weight of the aggregate. So I've got 19.17 feet times 100 pounds. I get 1,917 pounds for my coarse aggregate. And I've now completed step 17 where I've got my coarse aggregate in the overall mixture. I can now start to go ahead and I can start to determine the fine aggregate. And this is really where we start to get into accounting. And what we're going to do is we are going to take our simple example that we saw before, and we're going to start accounting for the different volumes. So we have the volume displaced by water in our overall system. We said that the weight of water was going to be 280 pounds per cubic yard. We know that water, we've got our densities of water, and we can convert that over. And we say that we now have 4.49 cubic feet of an overall yard of concrete is water. Our cement was 660 pounds. We know that's 196 pounds per cubic foot. We have 3.37 feet of this is going to be our cement. So we've got our water on the bottom. We now stack in our cement. Now the next thing that you may look at, and you may look at this and it may cause confusion, and I'm going to try to explain this very, very carefully and try to eliminate where the confusion comes from, but we can look at the volume of the coarse aggregate. And you may say, well, we just had the volume of the coarse aggregate. It was 19.17 cubic feet. Remember, that was the dry rotted volume. That incorporated the other space that was the pore space that was between the aggregates. Here what we're going to do is we're going to take our weight of our aggregates, our 1917 pounds, and we're going to divide that through using the actual specific gravity of the aggregate itself. So here what we're just looking at is what's really the volume of the aggregate itself, the hardened volume of the aggregate, and we're going to come up with our 11.83 cubic feet.
Why do you use 162 there instead of the 168 for the coarse aggregate? If you go back to the original problem.
I don't. If it says 160, let's jump back to the beginning, and I'll
slide 14.
If I've used the wrong number, it's merely because I did it wrong. The 168, it should be 168. So our numbers are going to be a little off, and I apologize. So this should be a 168 here. And now the number won't actually match up when you go to try to do the calculation, but it should be 1917 divided by 168, and it's going to be around 11.8. But again, remember that this number is going to be slightly off, and it's because, and I'll get this corrected and put it up on the website so that it's a corrected version so that we've got the right numbers in there. All right. Other questions? I apologize for that. This will be very confusing. I will come back and I will fix this part.
This is saturated surface dry.
Saturated surface dry. Yep. Now we can also go through and figure out how much of the system is taken up by air, and we said that we had 4.5% of the volume was air. 4.5% of our 27 cubic feet is 1.22 cubic foot of air inside of the system. And if we add all this together, we are going to find out that there is remaining space inside of the overall material. That remaining space is our empty space. That's the space that needs to be filled in by our fine aggregate. So that's how we're going to basically be able to determine our fine aggregate. And I've got this backwards here compared to what we had on the front page. So the weight of our sand will simply determine the volume. We'll be able to take the volume of our sand times the weight of our sand, and we'll come up with the overall weight that we would need for our fine aggregate in the system. And again, I will do the correction on this, but the basic principle is all laid out. The basic principle is the same. The only thing we need to do is put in the right number, and I apologize for that. Okay. So that's the end of step 8. Now, a few other things that I will mention before we start to jump ahead, and we'll come back to this later on in the semester. One of the properties that we're going to be very excited about is something called shrinkage. If we measure the shrinkage of our concrete, our loss of water will lead to a change in length. So what we will see is the concrete will be getting smaller over time because it's losing water. If we actually looked at the two constituents that make up our concrete, you would notice that the aggregate doesn't shrink a whole lot, where the paste shrinks an enormous amount. This leads us to the conclusion that shrinkage is a paste property. It's the paste that is shrinking. The aggregate is very happy staying stable. And one of the things that we need to point out here is that shrinkage is a paste property. The amount of shrinkage that a concrete experiences depends upon the volume of the aggregates. If it's 100% aggregate, we basically would have no shrinkage taking place, or very minimal shrinkage. If it's 100% paste, we would have the most shrinkage. And then what we will see is there is a line here, and this line is defined by something called Pickett's equation. And Pickett's equation tells us how much shrinkage we would have for our concrete as a function of the shrinkage of the paste times 1 minus the volume of the aggregates raised to a constant that's somewhere usually between 1.2 and 1.7. The specifics of this equation aren't really important. What's really important right now is that you get the basic concept that the higher the amount of aggregate, the higher the volume fraction of the aggregate, the lower the shrinkage. We could, instead of putting aggregate volume, we could also draw this where we had 0 down here, we have 100% over here, and we could say that this is the volume of the paste. So as the volume of the paste increases, so does the amount of shrinkage that we would experience, so does the amount of cracking that we could typically get in a field application, and we want to look at that. Again, as we start to see the water content go up, this typically means that we have more paste in the system. More paste in the system means that we're going to get shrinkage, and we'll generally talk about this a little bit later on in the semester. At this point, you would do any adjustments that you would need to in your particular mix to account for the fact that you may not have your aggregates in your saturated surface dry condition. I will give you an example of this. I'll put it up on the website because I don't want to spend lots and lots of time going through all the details on the adjustment of water, but I'll give you a worked out example of how to do this so that you can follow it. And then you would move forward and you would do a trial batch, and you would basically see if you got the type of performance that you wanted to look at. Now, what I want to do in the remaining part of this lecture is I want to give you a slight alternative to the type of approach that we've looked at here, and I will use this number frequently. I will use this type of approach frequently to get a good idea of a very quick estimate on what we may have in the system. This is an approach I saw Ken Hover use very quickly. Ken from Cornell uses this type of a graph. These are not his exact graphs. These are things that I've worked out, but these will match up very consistently with the graphs that you saw us presenting as we went through before. One of the things that you will notice is over here we've got Ken's table that comes out of the Concrete International paper, and then each one of these other graphs are graphs that we've seen up to a certain point. So what you will remember is that we started off, in the first step that we wanted to do is we wanted to look at the slump in our overall system. So we are going to enter this nomograph on the top portion of this particular the top portion of this graph up here where we've got our slump in inches. So for our particular problem, we may have a slump of 4 inches. We would draw a straight line down until we hit the maximum size aggregate curve that corresponds to 1.5 inch aggregate. So this is simply a graphical way to come up with the solution. Where it has intersected that 1.5 inch size aggregate, we could trace a line back across and get our water content, or we could extend that line over and we could get the water content over here on this other axis. Now, the real power here comes in that we've already determined, we've taken our slump, we've got our maximum size aggregate, we've determined our water content, and what we're going to do now is we are going to make a quick adjustment for the water that's inside of the quick adjustment for our water depending upon our particular mixture conditions. So there was a little bit of a question earlier, can you adjust these, can you add these up, can you take credit for, if you've got silica fume, can you put a water reducer in and get credit for it? Well, that's what you would do here. You would add all these values together. You would use the aggregate shape, the combined aggregate, the air entrainer, and I think we saw before that we would get like a 3% reduction in water. Here, if we have no reduction, we would simply use this green line that I'm tracing over, which is our 0% line, and we would turn and drop a perpendicular down to get to our next information on our mixture proportioning. However, if we were to adjust this, we could account for our water. So all of a sudden, if we said, well, we want a 10% reduction, we've added everything up and it's a 10% reduction, what we would do is we would move from this green line over to this new line that I've shown here sort of as this squiggly line, which is our 10% reduction, and we would drop our perpendicular from there. Okay, so it gives us a very quick way to do that overall water adjustment. So what you will notice is this is the actual water content that's listed on our y-axis. Our adjusted water content is listed up here on our x-axis, and it accounts for whatever you're taking into account on this particular adjustment here to account for aggregate gradation or anything else that's inside of the system. So if we adjust for 10%, you would see that we would drop this down. If we started off with something that was around 300 pounds per cubic yard of water, we adjusted it by 10%. 10% of 300 pounds is 30 pounds. 300 minus 30 gives us something near 270, which is exactly what we would pull off out of this graph. So what we've been able to do very quickly by using this graph, we take our slump, we drop down to our maximum size of our aggregate. Once we've got our maximum size of our aggregate, we can determine our water content. We've now got our water content. We can make any adjustments that we need to, and we can start to enter the next part of the graph, which is where we're going to be able to get quite a bit more information. Now, when we get into this graph, we will need to know our water to cement ratio. So for our particular application, you'll remember that it was 0.424 or 0.43. This was determined based on the strength of our system. So you could simply come in and say, for the strength that I needed, it was 4,700 psi. I could draw a straight line across, and I could pull off the water to cement ratio. The lower line is our air and trained concrete. The upper line is our non-air and trained concrete. And then you'll see a series of reminders for freezing and thawing, freezing and thin structures, sulfate, sulfate and thin structures, and then corrosion. They'll remind you that there may be other water to cement ratios that you might want to consider based on the exposure condition. Once you have that water to cement ratio, you will enter one of these lines, and these numbers correspond to water to cement ratio. So at 0.43, you're somewhere between the 0.45 line and the 0.4 line, and you would be right around in this range. That water to cement ratio would cause you to all of a sudden turn and look at our y-axis. That would be the amount of cement or the content of cement that's in the system. You could extend that over and read off the cement content. You'll remember from our previous example was 660 pounds per cubic yard. So we've gone through all the steps in a hurry. Once we get there, again, we can use our water to cement ratio, which is listed as these numbers above these particular lines. We find our water to cement ratio. We can drop a perpendicular, and all of a sudden we can start to see the volume of the aggregate that's inside of our overall system. So this is the sand plus the coarse aggregate, but we get a real quick indication of a lot of the parameters that are going into our mixture proportions. So one of the things that I may use a graph like this for is to determine something like a shrinkage cracking potential. We can all of a sudden take our mixture proportions in about 30 seconds without having to rev up the calculator and take out massive spreadsheets and do calculations like that. We can get an estimate on the aggregate volume, the paste volume, very, very quickly. So some of the examples we saw this example a little while ago. But we can start to go through and we can start to do some adjustments right now. We can start off our 4-inch slump, our 1.5-inch aggregate. We make no adjustment. Let's assume we have a 0.58 water to cement ratio that we're targeting. We would be down in this range, and we would come up with something like 72% aggregate by volume. If we make a slight adjustment to the overall system, we consider that we've got to have a lot of extra water because everything's gone wrong. We've got a real fine cement. We've got a real an aggregate with a whole lot of surface area. We've got a silica fume maybe in the system or something like that. We have to add a lot of water to the system. We can see that all of a sudden our slump isn't going to change because that's going to be dictated for us. Our initial water content's not going to change, but what does change is our adjusted water content. We've added 20% water to the system because of the fineness of our cement, the silica fume that may be there, the fineness of the aggregate. And we drop this down. Again, we still have our 0.58 water to cement ratio, but one of the things that we've noticed is we've gone from this 70% aggregate, and we've dropped it down to maybe 63 or 64% aggregate by volume. By making that simple change in our system, by making those simple adjustments to the fineness of the cement, coarseness of the aggregate, other properties, all of a sudden what we've done is we've increased the volume of our paste substantially by 5, 6, 7%. On the other hand, we could drop the volume of our paste by reducing the water, and we may be somewhere over in this range, up closer to 76, 78%. Now, it may not seem like a big difference. You're between 78% paste down to 64% paste, but there is a dramatic difference in the way that these two mixtures are going to behave. Right? One of them is 2/3 aggregate. The other is 80% aggregate inside of the system. And there's sort of a general rule of thumb that once you get outside of this shaded area here, once you get below typical numbers about 28% paste, once you get below, or once you get your aggregates below that 72%, or once you get the paste volume getting up above that, that's when you start to get into some problems where you may start to see some things like cracking. A lot more cracking, or the cracking may increase. So we've got, again, just a general, quick, fast way to go in and get a basic idea on our water to cement ratios, get a basic idea of strength, get a basic idea of some of our mixture proportioning, and turn out to estimate our cement contents, our water contents, and the volume of aggregate, or the volume of aggregate that we may have in the overall system. Okay, I'm going to skip through the example on mixture proportioning. I think you can go through and do that on your own if you want to. I want to take the last few minutes and I want to jump ahead if it's possible. And I want to start the discussion on water reducing admixture. So we talked a little bit about water reducers and the chemicals that can be used to reduce the water content and the water to cement ratios in our overall mixtures. And soon this will pop up for us. Questions before we jump ahead? Okay. So we'll wait for our water reducers to pop up. There we go. So we talked a little bit about shock. And we get back to this idea of our fresh concrete placement. We get back to this idea, this battle, where we've got something that goes from, what is it that we want to be placing? Do we want something that's incredibly fluid, or do we want something that may be a little bit more stiff? And we've got this battle that's going to dictate what we want to do. Here we've got a zero slump or negative slump concrete that's being placed behind a paver for a slip form operation. Here we have an operation where someone's using very fluid concrete, and we're really tempted to just add water, and the real reason we want to add that water is we really want to increase from our real low slumps up to our much higher slumps. And this is the battle that we were talking about last time. We're typically here talking about water of convenience, or water that's added on site to make the concrete a little bit easier to place, water that's mixed into the concrete to make it easier to place. This water is going to be problematic for us in the long term because this is going to be that capillary water that's going to dictate the strength and the overall durability of our concrete. So we said that we had this balancing act that we were talking about before. We wanted something that was fluid, it was easy to flow under its own weight. We wanted something that was stable, free from segregation, the age-old battle that's there. And really what we're trying to do is we're trying to address this balancing act. We talked a little bit about the fact that we're going to use a chemical admixture to change the surface charge on the cement particles, and it was going to be a lot like the Bounce fabric softener that we were talking about. The basic idea here is we're going to change the charge that's on the different cement particles so that they're not necessarily going to want to come in contact with one another. Now we'll talk a little bit more when we start to talk about SCC, about different types of water reducers that might be out there, but the basic general concept is that this is a dispersing agent or dispersive admixture, which is going to help to disperse the particles from one another. They're going to help to reduce the capillary voids that are going to be in the system. They're going to allow the particles to get closer to one another and reduce the size and volumes of the pores that we may see in our overall concrete. So as we reduce the porosity, our strength goes up. We get much more solid in the system, and we are going to increase our strength. Now, there are a lot of specialty admixtures that are out there. And the main classes of the materials that we're going to be talking about here they really fall into a few different categories. Most of them will be aqueous solutions. Some of them will be put into the grinding process. Specific gravity of these water reducers is going to be somewhere around 1.1 to 1.3. They're a chemical admixture that's covered in ACI 212. And in general, the only things that we're really typically worried about is the influence on the rate of hydration, and sometimes they can have a little bit of an interaction with our air and training admixture. So generally when we start to talk about water reducers, those are the two things that we're really kind of on the lookout. Now I mentioned that we were going to sort of use that we're going to sort of classify these materials in 3 separate ways. Our normal water-reducing admixture, commonly referred to as a plasticizer. Generally, we're looking at about a 5 to 10% reduction in our water. This can be used to give us a higher slump. But one of the things that we will come back to is typically we will see an increase in the slump loss over time. Now, slump loss, we're talking about the concrete. When it's out on site, it comes out with a 6 or 7 inch slump, and over time it becomes harder and harder to work with. Obviously, if you had a material that had a higher slump at the beginning, it's going to have a higher slump loss while people are working on it. So this is one of the things that we're going to come back and we're going to talk about. You will see people talk about increases in strength. The increases in strength come mainly because of the reduction in water to cement ratio. If you use this to alter your water to cement ratio, that's where you're going to see the increase in strength. If you maintain your water to cement ratio the same as it was before and just make the system more fluid, you're typically not going to see a big difference. The way that they work will depend a little bit on cement chemistry, so there'll be a little bit of a dependence on cement chemistry. You will also see that these materials will get either a label as being a type D admixture or a type E admixture, and this really relates back to how they relate to hydration. If they have a tendency to retard hydration because they're coating the cement particles with some sort of a film or something like that, they'll be a type D admixture. If they accelerate the hydration because they're dispersing the particles, creating more surface area that can come in contact with water, more surface area that can react, they will typically be referred to as a type E or an accelerator. The normal water reducers generally don't have a whole lot of interaction with air. They tend to be lignin-based, at least historically they were lignin-based. They started to change in recent years because of shifts in the industry, and they are less effective when you've got a lot of C3A in the system. The more C3A in the system, typically you're going to have to use more water-reducing admixture. Now, we saw the typical mid-range water reducer, our friend Homer. We said in the 1980s, when Rocky starts to come out, we see an increase in the use of different types of admixtures that were referred to as mid-range water reducers. These had about 6 to 12% water reduction. You may say 5 to 10%, 6 to 12%. What's the big difference? The main reason that these mid-range water reducers were being looked at was because they reduced stickiness. And stickiness is really what it sounds like. As you're finishing the material, the surface will feel sticky, and they changed the chemistry to try to account for this a little bit. Typically, the surface became a little bit more finishable, and that's really what they were after with the mid-range water reducers. The high-range water reducers are incredibly, very, very effective. You're going to see something like a 12 to 30% reduction in water. You may see some air issues. You may see some slump loss. You may also see some increased propensity for plastic shrinkage cracking because there's so much of a reduction in water here. I'm not going to get into a lot of the issues, but on almost all of these admixtures, what you will see is that there are a lot of claims on what the admixtures do. They'll knock your socks off, they'll make your socks whiter, they'll do all kinds of other things. Really, the main effect that we're seeing is all traced back to the water to cement ratio. All right, there is a little bit on how it alters the pore structure, but the majority of the effect is first seen as the water to cement ratio. So some practical considerations. Redosing the admixture on site can help to reduce things like slump loss. Repeated additions are possible. And the one thing that you may see is you may have some impact on the air system and bleeding, and this is typically a negative overall effect. Admixtures at the plant, you will see something that looks a little bit like this picture here. Here you can see a plant operator in probably the cleanest ready-mix plant that's ever been seen in the world. I don't know what this guy is looking at on that screen. I don't know if he's playing Space Invaders or what he's doing on the modern computer that's behind us. But one of the things that you will notice when we actually go on a tour of one of these facilities, you will look over to the side and you'll see these see-through canisters. And these see-through canisters are where the admixtures are going to be dosed. So you'll see these filling and emptying so that people can keep track of the fact that the admixtures are actually being added into the truck. So you'll see these fill up and they'll empty. One of the things that you need to be worried about, or need to be at least a little bit aware of, is as water leaves these systems, these materials can turn gummy and can cause some of the nozzles and things like that to stick open, which is one of the reasons why people try to keep a real close eye on what's going in and out of the trucks. Minimizing variation is really a key issue to using these. Most admixtures are furnished as liquids. One of the things that I will point out here is that because most of these are liquids, they need to typically be stored at a relatively warm temperature, which is another reason they're going to be stored indoors. They will be added typically just after the water, although this can vary depending upon the type of application. And the dispensing system we can talk about a little bit later. I'm not going to spend a whole lot of time going through here, but you'll see all types of different ways that these materials can show up. One of the things that I will point out is that if there's a lot of water in these systems, the transportation costs can be very, very high. So one of the things they try to do is minimize those costs. Now, the final thing that I want to get into today is I want to talk about 3 ways that you can use a water reducer effectively. In general, the performance improvement comes from a reduction in water-to-cement ratio, but really what we're talking about here is one of 3 ways. We're going to keep the same slump, get a lower water-to-cement ratio, and we're going to improve performance. We're going to use the same water-to-cement ratio, higher slump, and we're going to get better workability. Or the same water-to-cement ratio, and we can use that to lower the cement content and save some money. So what is it that we mean here? The first case of this is having the same slump and getting a lower water-to-cement ratio. So the basic idea here is slump is shown here as the flow table spread. This is the same type of idea. It's a measure of workability. We've got a curve that represents what happens when you've got a water reducer, what happens when you've got a plain water-to-cement ratio, or plain system. As you reduce as you move from the plain system over to the system with the water reducer, you will notice that we will drop the water content. As we drop the water content, you can either have the material with a higher slump, or you can basically come back to the material with the same slump and a lower water-to-cement ratio. So if we go with the same slump, I'm going to jump back through here. All right, if we've got our flow on our y-axis, we can have our plane, and I'm not even going to try to explain this because I'm going too fast and we're going to jump through it too quickly. What I will do is I'm going to take a step back. I am going to take 10 minutes to explain this instead of 1 minute and 22 seconds to try to explain this. And what I will do is I will pick up here next class, lecture 15, talking about admixtures and the 3 ways that they can be used at a speed that every other human being that listens to the English language can follow it at. And we are going to talk about these 3 main aspects where we're lowering the water-to-cement ratio to increase performance, we're increasing the slump to get concrete that's more workable, and we're lowering the cement content to make the mixture less costly and more economic. And that's where we'll pick it up next class. Okay?